is to get rid of the arbitrary metric, right? So Nobubuta action doesn't have an arbitrary metric, so we need to integrate out gamma AB. What that means in practice, we have to solve this equation of motion, right? We have to find a solution to that and plug it back in our original action, and then hope that what we'll get is going to be another good action. So notice that what we're doing here is we vary with respect to a matrix, right? So gamma AB is a symmetric matrix. And so what I'm going to do, I'm going to remind you, I'm sure you know all that, but just in case, I'm going to remind you, so the variation with respect to matrices. How are we going to do that? Well, so suppose I have MAB, so MAB is invertible matrix, and it's a symmetric one. It's important for me to have it a symmetric matrix, which is exactly the same as matrix that we're talking there. So with upper and lower indices, if I have that, that's one. Then what you can show is that delta variation with respect to M with the upper indices is M A capital A, M B capital B, delta M A B. So you would have thought that you can simply to go from delta M with upper indices is just the same as delta M with lower indices raised with symmetric answer. You would be wrong. There is an extra minus sign. Do you know, guys, how to derive this? Yes, all you have to do is just vary this identity and you will have 0. So that's one of the properties that we need. So the second property that we need, so if I'm going to call M, being a determinant of my matrix, determinant A and B, right? And so, what we will need, and you can see that in our action, there is a determinant of the matrix. What happens, how do I write down the fluctuation of determinant of the matrix? And so the answer is that it's M times MAB delta MAB. Okay, so there is this nice formula. Do you want me to derive it? One line. Remind you how to do it. So how does it go? Well, first of all, let me show you a nice let me remind you a nice identity. If I have log of determinant of MAB, so it's the same as trace of log of MAB. Okay? So all these traces and determinants tells me that the results are invariant. How do I choose my basis? So if it is a symmetric matrix, I can always choose my basis. So what I can do, I'm just proving you this identity or remind you. So what I can do, I can choose my basis so that A and B is non-degenerate matrix. So I can choose that is only a diagonal one, and then the statement is an obvious statement, right? So the first thing is a determinant is just a product. A log of a product is the sum of the logs. Okay, so that's the simplest way to prove that identity if the matrix is symmetric. But now once you have this matrix, I can do variation of both. Once you have this identity, I can put deltas on both sides. So if I put delta on the first side, I have a determinant. So I have M minus 1 variation of the determinant. And on the other side, I have MAB. So if I vary that, MAB must have an upper index now because it will be 1 over MA. You can always see in this diagonal basis. So I will have MAB and the variation of delta MA. Right, so what I did, I just proved you would say that.
I have a question. If some lambda is negative, so the log will define.
Right. So again, so this is I'm talking about. I have to talk about. Well, first of all, symmetric matrices, and then it should be stability should be hermetic, right? So that all the eigenvalues are positive.
But now you will talk about the metric. The metric is more intermediate.
So I have to put absolute values, and so that determinant I would have to put minus sign, and so I'll take care of that with putting a minus sign in front. But you're right. So simply speaking, this relation is true. This relation is this way of deriving it is. Well, yeah, I think I can go even for the matrix if one of the eigenvalues is negative. I would just have to have a minus sign in the right place. For the corresponding eigenvalue. Now, the reason I'm glossing it a little bit over, because so we do light cone, and that's pretty much the only time when we talk about Lorentz and Wolfschild. After that, we'll do analytical continuation, and all conformal field series are defined on Euclidean Wolfschild. So all our metric will be Euclidean. So I could have done it at this stage. Get rid of the minus sign in the metric. But let me keep it for the calculation. All right, guys, so we have this. So let's go ahead and now do the variation. Start here again. So vary with respect to this metric. So I'm not going to write down -1 over 4 pi, and I'm not going to write down the integral. So I'm just going to write down only the stuff that matters. So delta S P over delta gamma AB, right? So it's proportional to. Okay, very good. So so let me vary this guy first. So I have 1/2. I have 1/2 minus gamma, which is -1/2. And then I have -1 because I have gamma, minus gamma. And then I have to vary gamma, but that's a determinant of the matrix. So it's going to be equal times gamma. Gamma, okay, let me see the way how I'm writing down. Okay, so I'm just going to write down I'm going to write down one thing and then I'm going to immediately erase it. So that's a variation of their, so this -1 is here, and then this guy is a variation of their gamma, as given there. But what I'm going to do now I'm going to lower indices here, AB, and I'm going to keep up indices here. And once I do that, I need to put a minus sign in front because of that two, of the first two up there. Okay, so we have this, and so that's from variation of a square root of minus gamma, and then I have additional gamma up here, so I'll have plus square root of minus gamma, del A x mu, del B x mu, and then I have delta gamma AB. Okay, so very good. So then, so this equals to, sorry, what did I lose? This one? Oh, this eta?
Oh, in your first term.
Oh, yeah, sorry. Yeah, you're right. You're right. So then there is a, so let me do it this way. CD, so this is going to be CD, and then the guy must be multiplied by LA x mu, del B x mu, and I have kept 8. All right? Good. so that's equals. Right, so this guy here, and then there is minus gamma here. So I can erase this and put a +1 here, right? So let me do that. Okay. So now what I'm going to do, I will take out square root of minus gamma. Okay, so the first thing will give me minus 1/2, right? So then I have gamma AB del A x mu del B x mu here. And then I have left gamma CD with the down indices. Then from the second term, I will have plus del C x mu del B x mu. And then outside, I will have delta gamma CD. Okay? Good. So, did I erase that? There was a formula for the induced metric which disappeared. So, so when we talked about induced metrics, right? So remember that we introduced the induced metric is HAB, and so that's simply del x mu over well, okay, so this is just del A over x mu, del B over x mu. So this was just our induced metric, and I'm just going to use this as a shorthand notation to rewrite our variation. So this equals square root minus gamma. Then I have, as you can see, minus 1/2. So I have gamma AB times H. Sorry, gamma AB goes up. HAB, and then I have gamma CD plus HCD delta gamma CD. Okay, so you can see now that that if I'm asking that my action is stationary with respect to variation of gamma CD. Okay, so this guy equals to 0. So then, so that implies that the stuff in the square brackets equals to 0. So I have HCD must be equal to 1/2 gamma CD, and then I have gamma AB times HAB. All right, you with me, guys? Good. So, so I have this condition, and I'm saying that that's enough to see that the Polyakov action is the same as Navier-Stokes action. And the trick to do here is that, well, let's compute the determinant of both sides. So, so if we compute the determinant of both sides, so here I'll just have H. Right. Now, on the right-hand side, I have 1/2. That's a factor, but it's a 2x2 matrix. So when I'm computing a determinant, there will be a quarter. Now, this guy is just a constant, right? So it will simply get squared. Right? And then I have left a matrix, gamma CD, and that will be just a determinant of gamma. Okay? So now I have this relation, and I can rewrite this as square root of minus h, right, equals to 1/2 gamma AB HAB square root of minus gamma. So all I did, I just took a square root of that relation. And I included a minus sign because the determinant are negative. We're talking about Lorentzian bullshit. By the way, it's sort of related to your question. I'm sure that it's not the problem at this stage. Everything that we do works also for Lorentzian matrices you can modify. But the idea of making a path integral with Lorentzian bullshit is actually very difficult. And one of the things that can happen is that in Euclidean, for the Euclidean bullshit, the structure of bullshit is relatively simple, just determined by topologies, right? Now, in the case of Lorentzian bullshit, there can be a black hole in the bullshit. And I'm not talking about black holes in d-dimensional space-time. I'm talking about black hole on this 1 plus 1 dimensional field theory. This our 1 plus 1 dimensional field theory is a gravity, the theory of gravity. It includes metrics. So the instant you make a Lorentzian bullshit, you can create black holes. And so exactly sort of trying to go ahead and quantizing Lorentzian bullshit is very difficult. And I don't think it's been done. That's why what we end up doing is we don't end up doing an analytical continuation and talking about it. Very good. So we have that relation. And we are done. The reason why we are done is because I can show you that the Fourier correction is the same as Lambo-Boutroux action. So let's go ahead. So the Fourier correction, remember, is minus 1 over 4 pi alpha pi. So the integral over m, d tau d sigma. Then I have minus gamma AB, del A x mu, del B x mu. Okay, and so what I can do, well, I can, well, again, now here I'm substituting for the matrix gamma AB, the one that satisfies this condition. I don't need to solve that condition anymore, so I'm sure you can. So I have minus gamma, then I have gamma AB, then I have HAB, right? So because all this del AX, del PX is just the induced metric, HAB. And so you can see that what I have there is actually this structure up here. And so, if my metric gamma satisfies equations of motion, this is exactly the same. So gamma, I will say on shell, which by that I simply mean that it satisfies equation of motion, and this becomes minus 1 over 4 pi alpha prime, and integral d tau d sigma. Okay, and now this combination here is simply twice the square root of minus h. Right? There was the 1 half there. And so what we are having, this is minus 1 over 2 pi alpha prime, and integral d tau d sigma square root of h, and that's our Lambo-Boutroux. So we showed that at least classically, they're the same.
So one question, when you took the square root, in principle should put absolute values.
Right, but
Is it obvious that it's positive?
yes, it's positive because even if the metrics are Lorentzian, so this is like taking an inverse of the metric. Inverse of the metric and multiplying it with itself. So you will always get a positive number.
But if this Lorentz metric is sigma is time, tau is space,
Yes.
then it will be that.
No, because see, the induced metric will have minus along
I
tau
will
tau.
talk about gamma B.
Right, so yeah, okay, so there is this relation here. And I know that, okay, if we talk about Lorentzian bullshit, that both gamma and h are negative.
Yeah, but if for gamma metric,
Yes.
for H metric,
Yes.
the tau is time, sigma is space.
Yes.
And now if I choose such a gamma, that the tau is space.
Right, so the quick answer to your question is that you agree that there is a coordinate system in which this is the right thing. if I will say, so tau and sigma are arbitrary, and you agree that if I choose tau coordinate on the wall sheet to be exactly the same as the space-time time, then there is no problem.
Yeah.
Now, the statements, if you agree with that, then that's the end of the story, because all the statements here are invariant under the choice of coordinate system. They're invariant under reparametrization. So we just agreed with you that there is a special choice of how I choose the wall sheet time tau. If I make tau, right? So if I make the tau, which I'm free to make it any way I want, but if I say that tau equals to x naught, then all minus signs are aligned in space-time and on the wall sheet. And so there is no problem. But the thing is that the quantities that I'm discussing here, they are independent. They cannot depend on how I choose coordinate system. Right? See, the contraction here is the right contraction. It's invariant under reparametrization invariant. Those guys, H and gamma, they are determinants of symmetry. They're also invariant under reparametrization invariant.
But my question is, if you choose a set of coordinates, tau, sigma, now fixed tau and sigma.
Yes.
For this coordinate, the H for H matrix, the tau is time.
Yeah.
That's for
Yeah.
gamma matrix, the tau is space. So one is minus plus, one is
But it
plus,
doesn't.
minus.
But I'm saying that it doesn't matter how you choose coordinate system because you are computing determinants, and determinants are insensitive. What you exactly call tau and sigma. That's if you think what I'm saying that there is a coordinate system in which that's the right choice of signs, and I'm saying that all quantities here are invariant under diffeomorphism invariant, and the stuff that you're talking about are, different relabeling of coordinates. And the diffeomorphism group includes, in particular, you call tau and sigma, call it different names. Yeah, call what you call tau, call it sigma. All right, guys. So Nambu-Goto is the same as Polyakov, and right. So now we come to a very interesting stuff. It's not the same. So do you agree that it's the same? You agreed. I convinced you it's the same, but now I'm going to say that it's not the same. It's not exactly the same. It's not the same, but maybe if you think really, really hard about Nambu-Goto, actually, you will find out it's not the same, but maybe you will not. So, so let's see what I'm talking about. So now we deal with Polyakov action, and we ask the question. So what are the symmetries of the Polyakov action? So the first one, well, there are just pointer invariants. So x mu goes to x mu prime. I wrote this before. Mu plus mu. Then the second one is just reparametrization invariance. So, and again, we built it in such a way that our axes are scalars under reparametrization invariance, but gamma is a metric, right? So it must transform as I change my coordinates. And so the way how it transforms is in this way: dy c prime over dy a, dy d prime over dy b, and then I have gamma prime. So all the indices must be up for the coordinates. Get that. C equals gamma AB. Right, so that's the way how the metric must transform. The easy way to see this is the way how I always remember, is that whatever the transformations are, gamma, I have to keep forgetting to write down the right thing. So upper indices here, if I have prime, so this is a line element, it must be the same as the line element in unprimed coordinates. Right, so then you'll get the transformation rule. So for how the metric components transform. So it's invariant under Poincare, it's invariant under bullshit diffeomorphisms. 2, and that's the difference. Number 3. Number 3 is the difference that distinguishes, well, at least it's not manifest. It's not manifest in number Wood action, and some of you will tell me why. There is one more important symmetry of the Polyakov action, and this is number 3, very important. Okay, that's what means very important. And that's two-dimensional Weyl invariance. Okay, so what do I mean by that? So what do I mean by that? So I have to tell you how all our fields transform under the symmetry, and we all agree that that's indeed a symmetry. So well, our fields doesn't transform at all. Okay, so they are scalars, but the metric does transform. So my metric, while transformation is a rescaling of the metric, so this omega is an arbitrary function that depends on tau and sigma. So why does the Polyakov action invariant under this Weyl transformation? Well, the reason is that a square root of minus gamma, right, will go into a square root of minus gamma prime, which will be, so e to the 4 gamma, so it will be a square root of e to the 4 gamma, square root of minus gamma is going to be equal e to the 2 gamma square root of minus gamma. But then notice that I have gamma AB with upper indices, so it will go to gamma AB prime, which will be e to the minus 2 omega, gamma AB without prime. And so you can see that because of that, the square root of minus gamma, gamma AB, will go precisely to square root of minus gamma prime AB, and those two quantities are the same. So what we discovered is that there is this rescaling of the metric, and our action is invariant under this rescaling. Now, it's important that I emphasize here 2 dimensions. In fact, you can ask the question, well, you know, here we have 2 world-shape coordinates. What if instead of a string, you talk about a surface? Okay, I can take a surface, a table, and ask it to move in space-time. So it will span in space-time as 3-dimensional submanifold. And so I can write down similar objects there. It will be exactly the same action. And so what distinguishes 2 dimensions, that's what I want to get across. So for example, so let me write it down what I mean. So I could write, we can write SP for d-dimensional object. Right? So in particular, the action will look like SP tilde. So it will be whatever the tension minus the tension of this object, and then I can write down d psi 1, d psi d. Those are just coordinates on the world volume of that object. And then I would have square root of minus gamma, gamma AB, del A x mu, del B x mu. So I would have repeat exactly the same steps. So you can see that that's a 2-derivative action. It's invariant under Lorentz invariance, under Poincare invariance, but it will not be invariant under Weyl transformations. Okay, so it's not invariant under Weyl transformations unless d equals 2. And the reason for that is that I can repeat the same steps here. And so if I am in D dimension, so square root of gamma will go to e to the d times gamma, d times omega, square root to the minus gamma. But gamma AB with upper indices go to e to the minus 2 omega gamma AB, because that's just an inverse matrix. And so if I have e to the minus 2 omega, the inverse of that is e to the minus 2 omega. So in general, the square root of minus gamma, gamma AB, will go to square root minus gamma, gamma AB, e to the d minus 1/2 times omega. So in general, when I do a wild transformation on a d-dimensional action, it will not be wild invariant. So only when d equals 2, we have this special symmetry. And actually, what we will find out is that this is the symmetry that will be broken by quantum effects. And requiring that we do have that symmetry, even including quantum mechanics, we will get our critical dimension, we will get our 26, and we will get our graviton. In other words, I would like to claim that we wouldn't have a graviton without that. So now, the stupid question. Why Nambu-Butoh action? We showed that it's equivalent. It doesn't have this Y.
No gamma.
Exactly. We don't have gamma. In order to see this action, we had to allow an arbitrary metric rather than being made to the induced metric. Very good, guys. So, any questions up to now? So we understand the symmetries. So now, now the next step, yes.
This Weyl transformation is part of the parameterization event.
No, it's not, because it doesn't change coordinates. It would have been, in principle, there are some, but notice that what I'm doing here, I didn't put front. So I'm not changing coordinates. That's why it's different from diffeomorphic transformation. I'm not changing coordinates. All I'm doing, I'm taking a metric and scaling it. It's a very peculiar property. You can see that that's not the property that, for example, this action, in order to see the quickest way that what you're saying is not true, is that this action is always a parameterization invariant, but it's not wild invariant unless d equals 2. So this wild symmetry has nothing to do with diffeomorphic invariant. And the other way to see it, as I already mentioned, is that that transformation does not involve change of coordinates. Think of this as some additional global symmetry. But it's not really global because it depends on coordinates, it's a local symmetry. All right, guys, so next. So again, you told me you love Bohm. So the next thing is when you have a theory of gravity, we now understand that we need this metric, because without this metric, we don't have wild symmetry. So, but once you have a metric and that metric can fluctuate, you have a gravity. So we have a two-dimensional theory of gravity, a classical theory of gravity. And so we need to, once we start writing equations of motion, well, if you or if you involve, the next natural thing that comes about is that it starts talking about the stress energy tensor, right? So we're going to do exactly the same thing. And we're going to ask what is the stress energy tensor of our theory, and what are constraints on the stress energy tensor that are imposed by the symmetry. All right, guys. So let's go ahead. So in general, in QFT, quantum field theory, or classical field theory, if you give me the action, so if you give me the action S, I can compute, and typically we talk about quantum field theories in flat space-time, and you know how to compute stress energy tensor by using Noether methods. So, but you also probably have heard that the way to compute the stress energy tensor is to vary the metric slightly, even though it's a Minkowski metric. And so in particular, there is a formula that tells you, and you can go ahead and refresh Bolt, one of the appendices, that's the stress energy tensor of any action is 2 times square root of minus gamma. Actually, it's not that. It's 2 divided by square root of minus gamma delta S over delta gamma AD. Okay, so what I can do, I can take the action varies with respect to the background metric, and the variation gives me a stress energy tensor. Now, so this factor of 2, as you might have guessed, is just a convention in field theory, and in early days, string theorists wanted to be very special, so they came up with a different convention. So this is a way how we're going to define stress energy tensor in string theory. So in this case, on this two-dimensional quantum field theory will become quantum. So this is in string theory. So it's going to be equal to minus 4 pi over square root of minus gamma delta S protocol over delta gamma EB. So the only difference is a conventional factor of minus 2 pi. So that's it. So before we, so we're gonna compute the stress energy tensor of this two-dimensional theory. Up here, all we have to do is just vary with respect to the metric. But before we do that, I want to ask the questions, what are the conditions on the stress energy tensor that are imposed by the symmetries of the action, right? So constraints on TAB. If we assume that all the fields are on shell, constraints on TAB for physical fluctuations. Right, so the important thing is that when we write down the action, there is some field inside that action. It doesn't have to satisfy equation of motion. But what I mean here is that when I compute the stress energy tensor, I usually want to talk about physical fields. So I want to, it will be a functional, it will depend on the configuration of the field, but I want those fields to satisfy equation of motion. And so that's what I mean here. And what we want to do now is to ask, if I have a physical configuration, what are the constraints of the stress energy tensor? So the first thing that we're going to show is that diffeomorphism invariance, diff invariance on bullshit implies that TAB is conserved. So if I act with a covariant derivative, del A TAB, I will get 0. So that's the first condition. And the second condition, so this is diffeomorphism invariant, and then the second one is Weyl invariance, implies that. So this is a good condition. So this is like analog that the energy momentum is conserved, except that that's a condition now because they talk about theory of gravity. There is a gravity in two dimensions. So I must talk about, for non-trivial metric, I must talk about covariant derivatives instead of ordinary derivatives. Now, Weyl invariance implies that the stress energy tensor is traceless. The trace of it equals to 0. In other words, if I take A gamma AD and multiply by TAB, I should get 0. So those are the two conditions. And so what I'm going to do now, I'm going to show you that that's indeed the case. I might skip it, but I feel it's a good thing to actually see how to derive that. Would you agree with me?
Yeah. Are you taking the covariant derivative derivative in that action?
Yeah, so it's a good thing. So covariant derivative. So I wrote normal derivatives.
So these are normal derivatives, not
Well, there were normal derivatives, but what I'm going to do now is to replace that with a covariant derivative. And will it make it? It will make you happy. But for the guy who will not make it happy, would that guy feel a difference? That's a question for you guys. Is there a difference whether I put a covariant derivative there? Okay, the answer is no, that's the right answer. And the reason is why?
for 2 dimension. I think the critical symbolization.
No, no, because it's a scalar. See, if you have a scalar here, so let me remind you this. Okay. I'm just going to remind you everything I can, so that even if I don't go far enough, at least you don't have any questions about what we discussed. So, so if I have a tensor, right, and I take a covariant derivative, and I have some object, so it has lots of indices. I don't know. Let me call it I, and so here I have A, B, C, right? So how does the covariant derivative act? So this is del I, F, A, B, C, and then there are Christopher connections, right? So then there is gamma. So then I have gamma lambda, IA, and then there is F lambda, BC, and then there are 2 other terms, right? So if I have an index up, then it will be del I, FA, and then there will be, instead of minus, there will be plus. So here I would have A, and then I would have I lambda, F lambda. Okay, and if you have more indices, it would change. The only thing is that if this thing is a scalar, so if my object is a scalar, then the covariant derivative is the same as an ordinary derivative. Okay, so that's why there it wouldn't make any difference. Now, so this is a good thing to remind you. The good thing about covariant derivatives is that, well, metric depends on coordinates, right? So if I have something like, something del I, if I have del I, and this del I acts on, here I have, sorry, I'm running out of chalk. Okay, so here I have, say, gamma AB, gamma CD, square root of minus gamma, and then some function or some field, something like that. If I have an ordinary derivative, that would be a difficult thing to compute, because it would, so all these guys depend on coordinates, and I would have to add on gammas as well. However, if I have a covariant derivative, so the property of the covariant derivative is precisely such that action on the metric vanishes if your connection is compatible, is metric compatible. So if that is the case, then all this stuff I can simply, so this will be the same, square root of minus g, and I will just act on my function. So this is some of the properties that we're going to use in a second. Right, guys? So, good. So let's go ahead and see how those 2 properties, we're going to derive it without actually computing the stress energy tensor for now, and see that they are indeed the consequences of 2 things: physical fluctuations and symmetries. So how do we show that? Well, so the first thing is physical fluctuation. So for physical fluctuations, if I have fluctuations, if they are physical, they satisfy equation of motion. And so in particular, one equation of motion that is satisfied, delta S over delta gamma AB must be equal to 0. Okay, so if I vary with respect to the metric, then delta S over delta gamma AB is 0. Now, so let me start with the second one. So Weyl invariant, right? So under the Weyl transformation, So under Weyl transformation, what do I have? I have that, well, first of all, what are the Weyl transformations? Gamma AB goes to gamma AB e to the to omega. And so under these Weyl transformations, we showed that as particle goes to as particle. And this is for any, the important thing is this is true for any omega. And so in particular, this implies that delta SP over delta omega equals to 0, right? So if I try to vary the particle action with respect to omega, I will get 0. Now, but on the other side, you can see that Weyl transformation acts only on the metric, and so variation with respect to the omega, I can write down as variation is variation with respect to delta gamma AB, right? And then I have to times 2 gamma AB. Okay, is that clear? Because this, all I have to do, I just have to vary with respect to this. Okay, so very good. So what we have that 0 0 equals delta S particle over delta omega, which is 2 gamma AB times delta S over delta gamma AB, which is 2. And now I have to recall that my stress energy tensor TAB is going to be equal, is defined in this way, minus 4 pi over square root of minus gamma delta S over delta gamma AB. So this guy is the same, the variation delta S over delta gamma, and square root minus gamma over minus 4 pi times TAB. And so you can see that the invariance of the action with respect to the Weyl parameter omega requires that gamma AB TAB equals to 0. In other words, the stress energy tensor is stressed. So let me do the diffeomorphic one, and we will end for today. So the second thing is that we study invariance under Walsh-Diffie. And so we know again that delta as particle goes to as particle under diffeomorphic transformations, or in other words, what this implies is delta. Well, actually, what I said here, I don't need this. I will not need this. Okay, this is I will never need that. So delta S. So this is really just a consequence of the symmetries and nothing else. So if I know that my action is invariant under diffeomorphic transformations, then delta S over delta gamma AB, okay, must vanish, provided. So now I am putting a constraint, provided that that delta gamma AB is due to change of coordinates, right? So there is a variation of the metric which will be physically different from the one we started with. And then I can change a metric by simply changing a different, by changing coordinates, which is exactly what diffeomorphism invariance is. So now I'm putting a constraint on this delta gamma AB and saying that I look at the variations only such that they're due to change of coordinates. So what are those transformations on the change on the coordinates? Well, so at the linearized level, so on the whole sheet, I have coordinates y sub a, right? So now what I can do, I can say that y sub a goes to y sub a plus, I just need to take care of the indices. Okay, so here is the index up, right? Plus some function psi sub a. And so this function depends on tau and sigma, right? So I'm just making a small change of coordinates on a whole sheet. And so if I make this change of coordinates, I can ask how does my metric changes? And to linearized level, gamma AB goes to gamma AB. So you can look this in the Easter wall. So there is a covariant derivative here. Psi B minus delta B psi A. So that's how, or you don't even need to look at walls. So that's just do the change of variables and do it at the linearized level. And so you will find out that that's exactly how the metric will transform if you change coordinate. And so this tells you that at the linearized level, delta gamma AB is given precisely by this combination. So it's this, and for delta gamma AB with the upper indices, I would have simply plus. To raise this indices as well. Delta B psi A. Okay, very good. So so once we understood this, then we can do then we can vary the Polyakov action, right? And so the variation of the Polyakov action delta S, I can write down minus 1 over 4 pi alpha prime, an integral, right? So here, here I will have delta S over delta gamma AB, right? So the variation of the action with respect to the metric. But normally I would put an arbitrary metric, arbitrary variation of the metric. But I'm not going to do this. I'm just going to put the variation of the metric, which is due to this diffeomorphism invariant. Right? And because my action is invariant under reparametrization, so it must be equal, this stuff must be equal to 0 for arbitrary vector psi b. So now if I look what is here, so I have minus, actually I don't have this because I write out the action. So if I write, so what I have here, this guy is just TAB, right, with the upper index. I'm just going to put an index up here, and then upper index here, plus T and A. Okay. So then the stuff, this variation here will be 4 pi, square root of minus gamma. Then I have T TAB. I think I screwed up. Yeah. Square root of minus gamma over 4 pi. So the variation delta S over delta gamma just gives me the stress energy tensor. And then I have del A over psi B plus del B or B over psi A. And so this quantity must be 0 for arbitrary vector psi A. So if I look at this first piece up here, so I have del covariant derivative acting on psi, but I can integrate by parts. And so for now, I'm familiar with boundary terms. We'll go back and discuss it later. So now this covariant derivative, I can, as I reminded you, I can pull through the square root of the determinant. And so I will just have a minus sign in front. So I will have a square root of minus g over 4 pi. And then I have this covariant derivative active on TAE. And because stress energy tensor is symmetric, I'll just have a factor of 2. Both terms will give another contribution. And then I have to multiply it by psi b. And so this must be equal to 0. So because this is equal to 0 for arbitrary psi b, the only way it can be is that our stress energy tensor is covariantly constructed. Okay, so again, I'm emphasizing that these properties of the Wolfschild stress energy tensor, namely the conservation and the tracelessness, are just consequences of the symmetries that we impose. All right, guys, so that's it. And what we start doing, so next week, we will derive the stress energy tensor and explicitly show that, just derive the stress energy tensor. And then after that, we're going to go ahead and derive equations of motion and start quantizing the string and point particle in LIGO. Now, homeworks, after a little bit, we'll decide with you how many homeworks we'll have. And normally I would ask people to do from Polchinski some problems. And I'll do it the same.